Welcome to another deep dive. Imagine building a company that revolutionizes not one, but two entirely different industries,
Yeah.
almost dies multiple times, and then casually becomes the world's first $4 trillion enterprise.
Yeah, I mean, the sheer scale of that capitalization really challenges our baseline understanding of corporate growth.
Yeah.
We are looking at an entity that hasn't just captured existing markets, they've fundamentally altered the trajectory of global computing infrastructure,
Right?
and they survived multiple existential bottlenecks along the way to do it.
Today's stack of sources is just a treasure trove for understanding exactly how that happened. We are pulling from an exhaustive multi-hour interview with Nvidia CEO Jensen Huang on the Acquired podcast. We're cross-referencing that with Nvidia's fiscal year 2024 sustainability report.
Mm-hmm.
We also have detailed revenue breakdowns from Voronoi alongside some really critical geopolitical and market updates from The Guardian and the Ridgeway Record.
Our mission for you today is to basically deconstruct the architecture of the AI industrial revolution. We are going to unpack the technological and strategic pivots that took a company from rendering polygons for PC games to manufacturing the substrate of digital intelligence.
Yeah.
We'll examine the near-fatal crises of their early days, the contrarian bets that baffled Wall Street, and what their current dominance dictates for the future of global compute.
Okay, let's unpack this. Let's start with the current reality.
Mm-hmm.
Because the numbers are, well, they're almost entirely divorced from traditional corporate scaling. The Guardian reports Nvidia crossing the $4 trillion threshold, yet they maintain a global workforce of only around 40,000 employees.
That ratio of market cap to human capital is just unprecedented.
It's wild.
For context, you look at traditional industrial behemoths or even early internet-era tech giants, and they required hundreds of thousands of employees to generate a fraction of that valuation.
Right, like the old automakers or telecom companies.
Yeah, exactly. It speaks to a profound decoupling of physical labor from value creation. But the internal financial architecture is what truly reveals the paradigm shift.
Yeah, looking at the Voronoi data for Q3 of fiscal year 2026, the revenue inversion is stark. Data center revenue, that's the enterprise hardware powering artificial intelligence, reached $51.2 billion for the quarter.
Just for the quarter.
Just the quarter. That single segment now represents 89.8% of their total revenue. Gaming, which was the foundational business that kept the lights on for decades, accounted for just $4.3 billion.
A mere 7.5%. What's fascinating here is the velocity of that inversion. The Voronoi data highlights a 253% surge in data center sales over a 2-year window.
Wow.
And you juxtapose that against a 49% growth in gaming. This wasn't some gradual transition of resources.
No.
It was a structural reorganization of global capital expenditure. Tech giants were suddenly pouring billions into data centers, which completely validated Nvidia's $0 billion market strategy.
I'm glad you brought that up because the $0 billion market concept came up extensively in the Acquired interview. It runs counter to almost every traditional MBA strategy out there.
Oh, absolutely.
Usually, you identify an existing total addressable market and figure out how to capture, a percentage of it.
Traditional strategy is all about capturing existing demand. The $0 billion market strategy is about identifying a technological inevitability that currently has zero commercial demand.
Right.
You build the foundational ecosystem for it, and then you wait, sometimes for decades, for the market to materialize around your architecture. You aren't stealing pie. You are planting an orchard in an empty field.
Like a local bakery, right? Imagine
Yeah.
a neighborhood bakery that makes all its money selling bread.
Okay.
And they have this weird little side hustle where they cultivate and sell a very specific type of yeast. Nobody really buys it, but
Yeah.
they keep doing it.
Right.
And then one day, the entire global food supply chain collapses, and their specific yeast is the only thing that can feed the planet. Suddenly, their side hustle is an empire. That's what this feels like.
That's a great way to put it. But pulling that off requires immense conviction, especially when legacy giants are actively looking the other way. The Times of India ran a retrospective piece recently calling out Intel's $20 billion mistake from 19 years ago that has now become $3 trillion.
Which is wild to think about.
The source doesn't dissect the exact boardroom minutes, but the technological divergence is incredibly clear. The incumbent chipmakers were fundamentally bound to CPU scaling.
They were trapped by their own success.
Precisely. They were trapped by the success of sequential processing and the predictability of Moore's law. A central processing unit historically executes highly complex instructions sequentially.
One thing at a time, very fast.
Yes. The industry poured billions into increasing clock speeds and shrinking transistors to make that sequential execution faster. They viewed graphics processing, which requires calculating millions of simple pixels simultaneously, as a niche peripheral function.
Just something you plug in to play a video game.
Exactly. They completely missed the horizon where massively parallel compute would decouple from graphics and become the engine for neural networks. Because Intel and others were optimizing for sequential logic, Nvidia was able to quietly build a parallel processing monopoly.
There's an excerpt from Leafy Gaming titled NVIDIA's Strategic Pivot, from gaming GPUs to AI data center infrastructure. And it frames this not as a lucky accident, but as a highly orchestrated, multi-decade pivot. They saw the limitations of the CPU before the rest of the market hit the thermal and physical walls of scaling it.
They engineered the hardware for a post-CPU world and just waited. But getting to that position of luxury required surviving a moment where their entire architectural philosophy was proven catastrophically wrong.
Yeah, we can't skip over that. But to understand how they reached $4 trillion, we have to go back to a moment when they were worth almost nothing, and literally 6 months away from bankruptcy.
The year is 1997.
Right, 1997.
Their first two chips, the NV1 and NV2, were built on a fundamentally flawed premise. They bet on forward texture mapping and quadratic surfaces.
Which sounds incredibly technical.
Basically, they believed drawing curves was the mathematically superior way to render 3D graphics.
Which makes sense in theory, right? The real world doesn't have jagged edges.
It makes sense until the rest of the industry, and more importantly, Microsoft, goes in the exact opposite direction. Microsoft released the DirectX API, which established polygon rasterization drawing with triangles as the undisputed standard for PC graphics.
And just like that, NVIDIA's architecture is instantly obsolete.
Instantly, they were facing a market where 30 new competitors, companies like 3DFX, had fully embraced the triangle standard.
30 competitors.
And Nvidia was burning through their final 6 months of runway. They had to abandon their entire architectural philosophy and design a completely new chip from scratch, conforming to a standard they hadn't even built for.
So they bet everything on the RIVA 128. The goal was to build the world's first fully hardware-accelerated 3D pipeline. But the traditional semiconductor manufacturing process, the tape-out cycle, was a luxury they just could no longer afford.
Right, because in traditional silicon design, you tape out a prototype, wait months for the physical chip to be manufactured in a fab, then test it in the lab.
And you find a bunch of bugs?
Always. You find the inevitable myriad of bugs, redesign the silicon, and tape out again. It is a highly iterative, highly capital-intensive process.
And they had capital for exactly one tape-out.
Exactly. If the physical chip came back with a fatal flaw, the company would be liquidated.
So they adopted this process of extreme emulation. They acquired an emulator from a dying company called ICO. And this wasn't some sleek software solution you just install on a Mac.
No.
It was a massive physical piece of hardware. Essentially a supercomputer designed to simulate the logic gates of a chip that didn't physically exist yet.
They loaded the digital design of the RIVA 128 into this ICOS emulator and ran their software drivers against it to test for bugs.
Which is insane. Let me break down what emulation means in this context for you listening. It's like writing a blockbuster movie script, filming it, and editing the entire thing in your head before ever turning on a real camera.
Because you only have enough money to buy one reel of actual film.
Right. You have to get the whole movie right on the first take. The inefficiency of this process is just hard to overstate. The sources note it took something like 60 minutes just to render a single frame of an image.
Just brutal computational overhead.
Engineers were literally staring at monitors, waiting an hour, just to see if the Windows logo would render correctly.
And if a pixel was out of place, they had to dive into millions of lines of code, find the error, recompile the whole thing, and wait another hour.
The underlying philosophy here is what Jensen Huang describes as pulling future risk into the present.
I love that phrase. When you cannot afford failure at the execution stage, you must simulate the entire failure surface beforehand.
Yes.
By the time the digital design was sent to the fab to be printed into physical silicon, they had mathematically proven it would work.
I found Jensen's recount of this on the podcast so brilliant. When his team asked him how he knew the chip was going to be perfect, his response wasn't about the brilliance of the engineering or the math.
What'd you say?
He simply said, "I know it's going to be perfect because if it's not, we'll be out of business."
Extreme constraints breed extreme discipline. Because they pulled that risk forward, the moment the RIVA 128 physical silicon arrived, they bypassed traditional internal testing entirely.
They just shipped it.
They immediately shipped it to developers and reviewers, and it worked flawlessly. It saved the company and established them as a dominant force in the PC graphics market.
So they survived the crucible. But surviving isn't the same as dominating. To achieve the leverage we see today, they had to realize they weren't just making hardware. They had to transition out of being merely a component supplier.
This is the critical juncture where we observe the metamorphosis from a technology company into a platform company.
The distinction between those two is often blurred in tech media, but it's totally foundational to Nvidia's structural advantage.
A technology company sells a discrete product that solves a specific problem. A graphics card that makes a video game run faster is a technology product.
Right, you buy it, you plug it in, game runs better, done.
Exactly. A platform company, conversely, creates a foundational ecosystem. It provides the tools, the language, and the architecture upon which independent third parties can build entirely new businesses.
And the acquired interview reveals that Nvidia's original vision was actually to be a platform from the start.
Yes.
They wanted to build a multimedia console inside the PC, using their own API called DirectNV to compete with Sega and Nintendo.
But Microsoft's introduction of DirectX effectively crushed that ambition. DirectX became the platform, and Nvidia was relegated to being a hardware vendor executing Microsoft's code.
Which had to sting.
It did, but the lesson they internalized was severe. You cannot simply declare yourself a platform. You must first create undeniable, best-in-class technology, capture the developer mindshare, and systematically build the platform underneath them.
Here's where it gets really interesting. They began developing an abstraction layer, originally called UDA, which ultimately evolved into CUD.
Compute Unified Device Architecture.
Exactly.
If we connect this to the bigger picture, CUDA is perhaps the widest economic moat ever constructed in the semiconductor industry. Before CUD, if a researcher or developer wanted to use a GPU for non-graphics mathematics general-purpose GPU computing, they had to trick the hardware.
Trick it how?
They had to translate their complex scientific algorithms into graphic shading languages.
Oh, wow.
It was incredibly arcane. You're trying to calculate fluid dynamics, but you have to tell the computer you're calculating the color of a pixel.
That sounds like a nightmare.
It was. CUDA changed all of that. It allowed standard programming languages like C++ to interface directly with the parallel processing cores of the GPU.
And they established this non-negotiable architectural law. Every single GPU they produced, from the cheapest laptop chip to the most expensive supercomputer accelerator, had to be backward compatible with CUDA.
The financial discipline required to maintain that compatibility is staggering.
Because it wasn't free.
No, adding the logic gates necessary for CDA compatibility to every consumer gaming chip increased the silicon area. It drove up manufacturing costs and eroded their profit margins.
And Wall Street hated it.
Analysts punished Nvidia stock for years over this. They viewed it as a tax on the highly profitable gaming business to fund a scientific computing market that barely existed.
But because they absorbed that margin hit, they seeded the world with hardware. There are currently over 300 million active CUDA-capable GPUs in the wild.
300 million.
Yeah. They spent roughly 10,000 person-years of engineering effort developing this software stack long before the commercial machine learning market ever materialized.
They cultivated deep developer relations early on, too, courting pioneers like John Carmack of OOD Software, the guy behind Quake and Doom, to push the absolute limits of parallel compute.
So they basically built this massive parallel processing superhighway. And for a long time, only video game cars drove on it.
That's a great analogy. They had laid the tracks, but the train that would truly justify the infrastructure didn't arrive until 2012.
The 2012 ImageNet competition. This is universally recognized as the Big Bang of modern artificial intelligence.
The ImageNet competition was the crucible for computer vision. For years, researchers attempted to write explicit deterministic algorithms to identify objects in photos.
Like trying to mathematically define what a cat looks like.
Right, writing rules for how a cat's ears should look or how light reflects off a car bumper. The progress was agonizingly slow. Then, a team out of the University of Toronto deployed a convolutional neural network called AlexNet.
And AlexNet just shattered the previous benchmarks.
Completely destroyed them. And it did so not by having better hard-coded rules, but by utilizing two Nvidia GTX 580 GPUs to process massive amounts of training data simultaneously.
The profound realization that rippled out of AlexNet wasn't just about image recognition, though.
No, Jensen Huang recognized that deep learning wasn't just a neat feature for identifying cats. It was a universal function approximator.
That concept, the universal function approximator, it's dense, but it completely reframes how we think about computing.
To really grasp the magnitude of this shift, you have to look at the history of software engineering. Traditional programming relies entirely on causality.
Right.
A human developer must deeply understand the domain, deduce the causal relationships, and write explicit if-then logic to navigate them.
But deep learning abandons causality entirely in favor of predictability.
Precisely. A universal function approximator operates on the principle that if you map a sufficiently massive set of inputs to their corresponding outputs across a highly dimensional probability space, the neural network will approximate the underlying mathematical function connecting them.
It doesn't need to understand the why.
No, it only needs to optimize for the what.
Jensen illustrated this perfectly on the podcast. If retail data shows that a customer who buys a hot dog is highly likely to buy mustard, we do not need to model the complex psychological or cultural causality behind that pairing.
We don't need to know why they want the mustard.
Exactly. We simply apply the function to predict the behavior. The same applies to infinitely more complex systems, weather, toothpaste, movies.
Weather simulation is the prime example. Humanity understands the Navier-Stokes equations governing fluid dynamics, but calculating every molecular interaction of the Earth's atmosphere deterministically is computationally impossible.
It would take forever.
But if you feed decades of global weather telemetry into a universal function approximator, it can predict atmospheric outcomes with astonishing accuracy without calculating the explicit physics of every molecule.
So if software can now write itself through exposure to data, the very nature of software was about to change. Every application in every industry would eventually be rebuilt on neural networks.
And if the software fundamentally changes, the physical computer required to run it has to change too, and that leads to a massive pivot.
By 2015, when OpenAI was founded as a nonprofit research lab, Nvidia recognized they were pushing the vanguard of this new compute paradigm. Jensen personally delivered the first DGX-1, which was a dedicated integrated AI supercomputer directly to OpenAI's offices.
That delivery marked the transition from selling components to selling data centers. They had to reimagine the computer.
So Nvidia realizes the computer doesn't need to sit next to the monitor anymore.
Right. The transition began conceptually with cloud gaming. GeForce Now was their initial foray into realizing that the compute engine no longer needed to reside locally under a user's desk. The rendering could happen in a centralized server and stream to a thin client.
But hosting video games in the cloud is a fundamentally different engineering problem than training a large language model.
Yeah.
The sources draw a really sharp distinction between hyperscale computing and distributed computing.
And understanding that distinction is the key to understanding NVIDIA's current monopoly. Hyperscale computing is the architecture that built the modern web. Google, AWS, Meta.
Okay.
It is designed to handle millions of independent stateless requests simultaneously.
So if I search for a recipe and you stream a video,
Those tasks do not need to interact. They are processed on independent servers connected by standard commodity Ethernet. If one server fails, the system just routes around it seamlessly.
but AI training is not hyperscale. AI is distributed computing.
It is the antithesis of hyperscale. AI training is a single, monolithic, unbelievably complex mathematical operation backpropagation across billions or trillions of parameters. You cannot fit that model on a single chip. You must shard the model across thousands or tens of thousands of GPUs.
And here's the bottleneck for you listening. All of those GPUs must constantly synchronize their calculations.
Exactly. If 10,000 GPUs are calculating a gradient update, GPU number 1 cannot proceed to the next step until it receives the results from GPU number 10,000.
And in a hyperscale environment, standard Ethernet introduces unpredictable latency.
Yes, if one packet of data gets delayed by a microsecond, the entire 10,000 GPU cluster stalls waiting for that data. This is known as the tail latency problem.
So the network itself basically becomes the computer. The processors are completely useless if the data can't move between them fast enough.
To solve the tail latency problem, Nvidia executed what will likely be remembered as one of the most vital acquisitions in tech history, the $6.9 billion purchase of Mellanox in 2019.
Mellanox was the pioneer of InfiniBand, this high-throughput, incredibly low-latency networking standard.
InfiniBand bypasses the traditional operating system kernel. It allows direct memory access between devices across the network. The interview discusses the physical limits of networking the speed of light.
Right, which I love this part. The speed of light end-to-end across the planet is only about 120 milliseconds.
So the physics of light isn't the bottleneck in a data center?
It's the traffic jam.
Yes, the bottleneck is the switching architecture, the software overhead, the collisions of data packets. InfiniBand strips out that overhead. It allows a cluster of 30,000 GPUs to operate mathematically as a single, massive, instantaneous brain.
It's like standing near the tree waiting for the apple to fall. Nvidia wasn't exactly sure when LLMs would explode, but they acquired Mellanox so they'd be the first to catch the opportunity.
Another instance of planting an orchard in an empty field. They integrated networking into their stack years before the broader market understood that LLM training would require entirely new data center topologies.
To build an entirely new type of computer, Nvidia had to build an entirely new type of company.
Designing and deploying infrastructure at that scale and at that velocity requires an organizational structure capable of processing information without degradation.
Which brings us inside the machine itself. How does a company operating at the absolute frontier of physics and computer science organize its human capital?
Well, traditional corporate governance heavily relies on hierarchical command and control structures. Information flows from the CEO down through layers of middle management.
And it gets summarized, filtered, and usually distorted at each layer.
Exactly.
Nvidia explicitly rejects that model. They are not built like a military command. They architected their organizational chart to mirror a computing stack.
Have you heard of Conway's Law?
Explain it for us.
Conway's Law states that organizations design systems that mirror their own communication structures. If you have a siloed, bureaucratic organization, you will build siloed, inefficient software.
That makes total sense.
NVIDIA requires deeply integrated, holistic systems. The GPU, the CUDA software, the InfiniBand networking must all function as one unit. Therefore, their management structure must be entirely flat and highly integrated.
Jensen Huang manages over 40 direct reports. 40.
For anyone who has studied organizational behavior, a span of control of 40 direct reports violates every principle of traditional management theory.
It's supposed to be unmanageable.
It is unmanageable if the CEO's role is micromanagement and resource allocation. It works at NVIDIA because of a principle they call mission is the boss.
Power and authority are decoupled from corporate titles.
Exactly. The pilot in command for any specific initiative is the individual with the highest context and technical capability for that specific problem, regardless of their rank on the HR chart.
By flattening the structure, they eliminate the information silos that plagued legacy tech companies. The acquired interview highlights that strategic decisions and contextual shifts are communicated simultaneously to executive vice presidents and new college grads.
There is no hierarchical hoarding of information.
Imagine being at a company where you, on your first day, get the same strategic information at the exact same moment as the executive team. That's how NVIDIA operates.
It ties directly into their core values from the sustainability report. Speed and agility combined with intellectual honesty.
Because you cannot have agility if ground truth data is being filtered by middle managers trying to protect their turf.
No, intellectual honesty requires the entire company to look at raw data, admit when an architectural bet is failing, and pivot instantly.
The empirical evidence that this intense, flat structure works is found in their retention metrics. The sustainability report reveals a global turnover rate of just 2.7%.
Which is an astonishing anomaly when you benchmark that against the broader semiconductor and tech industry average, which is around 17.7%.
They don't just retain talent. They cultivate an environment that supports it holistically. The report details significant investments in workforce diversity and learning. 50% of their board of directors is diverse. Pay parity has been achieved.
They offer an allyship program.
And they offer 8 free recharge days annually, recognizing the intense cognitive load of their work.
Yet we must acknowledge the sheer human toll of navigating these technological shifts. Jensen Huang's reflections on the podcast provide a sobering counter-narrative to the glamour of a $4 trillion valuation.
He explicitly stated that if he could rewind the clock to age 30, knowing the absolute agony, the vulnerability, and the deeply public embarrassments required to build a company.
He wouldn't do it again.
He wouldn't. The superpower of the entrepreneur is almost a necessary delusion. If you truly understood the difficulty of the path, you would never take the first step.
He attributes his survival not just to his own resilience, but to a 30-year ecosystem of support. Co-founders, deeply loyal employees, and venture capitalists who held the line during the darkest periods.
Like Don Valentine from Sequoia Capital.
Yes, the anecdote about Don Valentine perfectly encapsulates the era. When Valentine agreed to fund the early, highly precarious iteration of Nvidia, his condition was stark. He told Jensen, "If you lose my money, I'll kill you."
Which is funny, but terrifying. It's delivered as a joke, but the underlying stakes were absolute.
That crucible forged a company culture capable of executing the transition to the Fourth Industrial Revolution.
Which brings us to the future. This unique structure allows them to build the future at lightning speed, and that future is focused on the Fourth Industrial Revolution. Generative AI shifts computers from being instruction-driven to intention-driven.
We define the First Industrial Revolution by steam power, the second by mass production and electricity, and the third by digital computing and the internet. The fourth is defined by generative AI.
So, instruction versus intention.
For the past 70 years, the barrier to computing has been translation. Humans had to learn arcane programming languages, C++, Java, Python, to instruct machines on exactly how to perform a task.
Line by line.
Generative AI models act as a universal compiler. You provide the machine with your intention in natural human language, and the universal function approximator handles the execution.
But democratizing compute on that scale inherently creates a massive surge in energy demand. The media focus on the power consumption of AI data centers is intense.
The energy footprint is a massive engineering constraint, and the sustainability report tackles it directly. The framework they use requires a longitudinal view of energy consumption.
Right.
The immediate training phase of a trillion-parameter LLM undeniably requires staggering megawatts of electricity. However, the subsequent inference phase, applying that trained model to solve global optimization problems, generates exponential energy savings.
The report highlights a collaboration with Microsoft and the Pacific Northwest National Laboratory that perfectly illustrates this leverage.
Materials science is traditionally an incredibly slow trial-and-error physical process.
Right.
By deploying accelerated computing and AI models trained on quantum chemistry, researchers were able to computationally screen over 32 million potential molecular structures for a new battery material
32 million.
in roughly 1 week. And they isolated a candidate that could reduce the need for lithium in battery production by up to 70%. So the energy expended by the GPUs during that week of calculation is just a microscopic fraction of the global energy and carbon emissions saved by revolutionizing lithium extraction over the next decade.
Precisely. Similarly, AI models are being deployed at the edge in smart electric meters to dynamically balance power grids, predict peak loads, and optimize the integration of intermittent renewable energy sources like wind and solar.
Nvidia is also driving immense efficiency at the silicon level. The new Blackwell GPU architecture is engineered specifically for these massive workloads. For certain high-performance computing and AI inference tasks, Blackwell delivers a 20x energy efficiency improvement over traditional CPUs.
A 20-fold improvement. The manifestation of that efficiency is visible on the Green 500 list, which ranks supercomputers by their energy efficiency.
Nvidia powers 7 of the top 10 most energy-efficient systems globally.
But the most ambitious manifestation of intention-driven computing is Earth 2. They are building a digital twin of the entire planet inside their Omniverse platform. We discussed the limitations of traditional fluid dynamics for weather prediction earlier. Earth 2 utilizes physics-informed neural networks.
By training the AI on decades of highly granular European weather data, the system can predict complex atmospheric interactions, wind shear, barometric pressure, precipitation at a 2-kilometer resolution.
And it does this with terrifying efficiency.
Right.
The sources note it operates 1,000 times faster and 3,000 times more efficiently than legacy physics-based supercomputer models.
It transitions climate modeling from a reactive observational science to a proactive, highly granular predictive tool for mitigating natural disasters.
So what does this all mean? If AI is accelerating material science, optimizing global power grids, and predicting the climate instantaneously, aren't we just engineering our way out of having to work?
That assumption ignores human nature entirely. The acquired hosts introduce a concept they term the Moritz corollary to Moore's law.
The historical precedent is clear here. As the cost of a resource drops to near zero, Demand for it becomes infinite. It's related to the Jevons paradox in economics.
When steam engines became more efficient, coal consumption didn't decrease.
Right, it exploded because steam power was suddenly applied to entirely new industries.
Exactly. As the marginal cost of intelligence trends towards zero, human ambition expands to consume the available surplus. If an AI can write a complex software application in 10 seconds instead of 10 weeks, the engineer doesn't take the rest of the quarter off.
They prompt the AI to build 100 applications.
They tackle problems that were previously ignored because the compute cost was prohibitive.
NVIDIA's internal operations reflect this aggressive push to support expansion sustainably. In FY24, the company successfully sourced 76% of its operational electricity from renewable resources.
Their physical footprint, specifically the massive Voyager and Endeavour headquarters in Santa Clara, are LE Gold certified.
Furthermore, they are optimizing the physical distribution of their hardware, ensuring that over 90% of the packaging for their massive GPU server racks is manufactured from recyclable materials.
But wielding this much power on a global scale comes with intense geopolitical and ethical responsibilities.
Operating at the center of the Fourth Industrial Revolution automatically places the company at the epicenter of global geopolitical tension.
The reality of being a $4 trillion entity is that your supply chain and your customer base are inherently entangled in statecraft.
The Guardian reported on NVIDIA's complex negotiations regarding trade policies and tariff regimes under Donald Trump's administration, specifically concerning the tech trade war with China.
As an enterprise, their mandate is compliance and supply chain resilience. When export controls restrict the bandwidth capabilities of chips sold to specific regions, NVIDIA must dynamically re-engineer their silicon architectures
Developing compliant variations like the A800 or H800 series.
to maintain access to global markets while strictly adhering to international law. Navigating shifting tariffs, export bans, and diplomatic fluctuations is a daily operational reality for their logistics and legal teams.
And their supply chain complexity goes much deeper than just the final sale of the chip. NVIDIA operates as a fabless semiconductor company.
They design the hyper-complex logic of the GPU, but they do not own the physical foundries, the massive multi-billion-dollar factories that print the logic onto silicon wafers.
They rely heavily on partners like TSMC in Taiwan for physical manufacturing. Because they lack direct ownership of the foundries, their primary leverage for ensuring global responsibility lies in rigorous supply chain auditing.
The sustainability report outlines an aggressive approach to Scope 3 emissions, the indirect greenhouse gas emissions that occur throughout their value chain.
Currently, 60% of their supply chain is actively engaged in tracking and reporting carbon data. Beyond carbon, they have audited 93% of their direct suppliers over the past 2 years.
To ensure strict compliance with international human rights standards and the ethical sourcing of critical conflict minerals like tantalum and tungsten.
Beyond the physical hardware, there is the existential engineering challenge of the software itself. Building the substrate for digital intelligence raises critical safety parameters.
This raises an important question. In a fundamentally probabilistic system like a large language model, how do you enforce deterministic safety constraints?
Right.
If the system is a universal function approximator, predicting the next token, how do you guarantee it doesn't hallucinate malicious code or biased outputs?
NVIDIA addresses this through their Trustworthy AI, or TAI, initiatives. A primary component of this is NeMo Guardrails.
NeMo Guardrails is an open-source toolkit designed to establish programmable boundaries around an LLM. It allows developers to dictate strict semantic boundaries,
Ensuring the model remains on topic, executes only authorized API calls, and filters out malicious or dangerously inaccurate responses before they reach the user.
They are also pushing for deep transparency regarding how these models are built in the first place, using an enhanced framework called Model Card++.
A model card functions similarly to a nutritional label for an AI model. Model Card Plus expands this by providing rigorous, standardized documentation detailing exactly what data sets the model was trained on.
The inherent limitations of that data, safety evaluations, and known biases. It forces developers to declare the operational boundaries of the intelligence they are deploying.
Furthermore, they're actively addressing the systemic tensions regarding intellectual property and generative AI.
Rather than adopting the prevalent industry practice of indiscriminately scraping copyrighted material from the open internet, NVIDIA has engineered partnerships with intellectual property powerhouses like Getty Images and Shutterstock.
These partnerships are designed to train generative models on fully licensed, legally vetted datasets.
Establishing frameworks where original creators are fairly compensated for the data powering the AI, it is an attempt to align the rapid acceleration of generative AI with existing commercial and legal structures.
And running through all of these safety protocols is Jensen Huang's overarching philosophy regarding autonomous systems, the absolute necessity of the human in the loop.
The consensus is that high-agency AI systems capable of not just reasoning but taking independent action cannot be deployed into critical infrastructure without massive redundancy and validation.
Much like a commercial airliner, possesses highly sophisticated autopilot capabilities, but still requires human pilots to manage edge cases and context shifts.
Powerful AI requires continuous human oversight, diverse validation metrics, and the inability to alter its core parameters in the wild without human consent.
The journey we've tracked today spans a staggering evolutionary arc. Let's recap the architectural shifts that defined this deep dive.
We examined a company that stood on the brink of absolute failure in 1997. By embracing the extreme constraint of a single tapeout and validating the RIVA 128 through agonizing emulation, they pulled their future risk into the present and survived.
They refused to remain a commoditized hardware vendor. They absorbed years of margin compression and Wall Street skepticism to build CUDA, a massively parallel computing platform.
Laying the foundation for a $0 billion market that wouldn't arrive for over a decade.
When the AlexNet breakthrough occurred, they possessed the unique structural vantage point to recognize deep learning not as a graphics anomaly, but as a universal function approximator that would transition computing from deterministic causality to high-dimensional predictability.
They realized that processing massive neural networks required distributed synchronous computing. They acquired Mellanox to bypass the limits of standard Ethernet.
Utilizing InfiniBand to transform the network itself into the computer. And they executed all of this through a flattened, non-hierarchical organizational OS where the mission dictates authority.
And now they are the foundational architects of the intention-driven computing era. They are driving unparalleled energy efficiencies in silicon to power innovations like Earth-2.
While simultaneously attempting to rigorously bound the safety and geopolitical complexities of their technology. Thank you for joining us on this exploration.
If there is a singular truth to extract from this massive stack of sources, it is that Nvidia didn't simply engineer a faster processor. They engineered a mechanism to simulate the future, built the infrastructure to support it, and waited for the rest of human ambition to catch up.
Jensen Huang noted that humanity has infinite ambition.
We've just handed ourselves a tool, digital intelligence, that can theoretically scale to match that ambition. If AI can solve our deepest logistical and scientific bottlenecks, from the power grid to the weather, the question isn't just what jobs AI will replace.
The real question is, what entirely new frontiers of human endeavor will we invent now that the friction of computing has vanished?
That's the challenge for the next generation.
A massive question to chew on as the computation continues to scale. Keep questioning, keep exploring, and we'll catch you on the next deep dive.